Hello and welcome to our first LeetCode problem. Um, I'm excited. We have a long journey ahead of us, or a long, exciting journey. But we have to have some humble beginning, and this is it. We're going to start with the very first question on LeetCode. Um, so without further ado, let's get straight in. Reading the question, given an array of integers, nums, and an integer target, return indices of the two numbers such that they add up to target. Okay, seems pretty straightforward so far. We have a list of numbers and we have a target, and two numbers inside the array have to add up to the target, two numbers. Okay, you may assume that each input would have exactly one solution and you may not use the same element twice. Okay, so that means there must be an answer to our question and you cannot use the same number twice. Okay, so let's take the example then. 2, 7, 11, and 15. Okay, so um, we can solve this pretty simply with a brute force approach. All we have to do really is look at all the numbers inside of our array and then compare them to the other numbers. So for example, if we start at 2 and we try to compare it to all the other numbers, we would say, does 2 plus 7 equals 9? It actually does, so we found our answer. Our answer would actually be, let's see, 0, 1, 2, 3. These are the indices in our array. The answer would be 0 and 1, right? 0 and 1. Let's do the other example real quick. 3, 2, and 4. Let's try our algorithm the same way. Let's compare 3 and 2. 3 plus 2 is 5. Our target is 6, so it's not right. Let's go to the next number and compare it with 3. 3 and 4 is 7. So we did 3 and 2. Now let's try 3 and 4. 3 and 4 is 7, not 6. So again, wrong. So now instead of a starting point of 3, let's take 2. But we don't have to go backwards anymore because, going forwards we already did all the numbers prior to this to the numbers ahead of it. So we just go ahead and we say there's 2 plus 4 equals 6. It does. So that would be our answer. Our answer would be 0, 1, 2. Our answer would be index 1 and index 2, right? Index 1 and index 2. Okay, great. We're essentially looping through these arrays once to get our starting number, and then we're comparing that starting number to all the numbers that follow. And if we don't find our target, we take the next starting number and compare it to all the other numbers that follow again until we find our target. So we're looping through the numbers once and we're looping through them again when we do our comparison. So how would that look in actual code? So we described two for loops. The first for loop is going to be looping through the array once, starting with the first element, aka 0. We're looping through the entire array, num size, I++. And after we loop through the first time, which is to get our starting number, we need to, with each starting number, compare it to all the other numbers. So we need to have another loop. So int j is equal to I plus 1. And the reason we have I plus 1 and not 0, aka the first number in the array, is because first of all, we aren't allowed to use the same element twice, as the problem said. And you'll remember the way we actually did it in our examples before is that we would compare the current number, the number that we chose, our starting number, if you like, to all the other numbers starting with the next number. So I plus 1 will give us the next number. And then again, we want to loop until we get to the end of our array. And then we also want to obviously increment this loop regularly. Why did that indent so strangely? Okay, there we go. Okay, so now we always have the position of two different elements in our array. So now we can compare those elements and see if at those indices, those two numbers add up to get a target. So what can we do? We say if nums at position I plus nums at position j is equal to our target, then we've actually found our answer. And we probably want to store this in an array, right? Because our output needs to be two numbers, and that looks like it should be an array to me. So our array, our first number in our array will be I, and our second number in our array will be j, right? So all we need to do is, and then we can return the answer, return result. All we need to do is a little bit of housekeeping, and first of all, create our result, create our array, I should say. um, me to get some memory from the OS, ask for some memory. So we want to say it's the return size times size of int. And what return size is this argument we're actually being given into the function. And what that is the size of the array that we're creating here. And the size of this array, or how many elements we have in the array, or how many elements we have in the array, is actually always going to be 2, right? There's only 2 numbers that add up together to the target, so this should always be 2. Um, and this should be our answer. We do need to return result at the end again here, even though there is exactly one solution, which means we will always have an answer, which means this should technically always give us a result. The compiler doesn't actually know that the user is guaranteeing, or whoever is giving us this data is guaranteeing that there will be an answer. The compiler has no idea. So whenever the compiler analyzes this code, it will see that we can return result here, but what if we never kind of get here? Then we need to return result somewhere else, because we always need to return something from a non-void function. So we also need to return result here so the compiler doesn't complain. I did just notice that I named this variable incorrectly. It's not result size, it's return size. I don't know why I called it that. Okay, return size. Our time complexity for this algorithm we've created would actually be O of n squared, or O to the power, or n to the power of 2, right? And the reason that is first of all, in this first loop, we loop through num size, the number of elements we have in our array. And then within that loop, we're actually looping through num size again. So this is actually, with regards to time complexity, quadratic. It's O of n squared with these 2 loops. And space will be constant. So our current time complexity is O of n squared. How can we possibly make this faster? That's a question mark, by the way. I'm making it look like a weird hieroglyph. Okay, how can we make this faster? Still looks weird, but anyway. Let's look at our first example again. We have 2, 7, 11, and 15. Okay, so what have we done so far? So far in our algorithm, we took every single number and we compared it to every single other number until we found our pair. Well, what if we could take a number and we could know the corresponding number, the pair that we need to get to the target ahead of time? Well, we can actually do that. We know that our target is 9. So if we say 9 minus 2, we get 7. So we know that if we have 2 and 7 in our array, then we have already found the pair, right? The answer to our problem. So how do we actually find that corresponding pair in an efficient way? Well, we need to use hash tables. First of all, we would need to fill our hash table with the numbers in our array by passing over these numbers one at a time and passing them into some kind of hash function. So we'd pass in our 2 and we'd get a hash number, and then we'd get another hash number when we passed in our 7, and so on and so forth, right? All we would have to do, right, after we filled our hash table is pass in these numbers one more time into our hash function. But instead of passing in just the number on its own, we would pass in the target minus the number, and we would get really the hash of a number that we may have already put into our hash table, so hash 7. So in this case, we know that we filled our hash table with this hash 7 entry. So whenever we look for hash of 9 minus 2, we should get a hit on our hash table, meaning that we already have the pair. Then all we need to do is use the indexes from those 2 numbers to get our answer. So how do we actually implement this in code? So one of the things we talked about is having a hash function, which we're going to have to implement. I'm going to use a very simple hash function. We'll just call it hash. And in we're going to pass in our values in our array. And in return, we should just get our hash number, which will be our entry in our hash table. So I'll just say value modulus prime number. This is a really simple hash function. Just for demonstration purposes. And we're going to define prime number as some prime number, which is also going to be the size of our hash table. Okay, so we want to create our hash table, and each entry in our hash table is going to have to be represented by some kind of node, which holds our data, right? It needs to be a node to hold our data. Potentially, we need to make a linked list from that node. So we want to store our index in here, and we're also going to want to have a pointer to another node um, in case we need to create a linked list here. Okay, so now we should be ready to create our hash function, our hash table. So let's do that. Let's call it hash table or HT, and we'll get some memory for it. So we'll have to call malloc again, node uh, malloc, and we want to say size of one of our nodes, and we want to multiply that by how many entries we have in our hash table. So prime number. Okay. So first of all, we need to make sure our hash table is empty. So we're going to want to have some kind of init hash table function, which will pass our hash table into. Let's write that up real quick. And we avoid init hash table. We're going to pass in our actual hash table, node hash table. And all we want to do here is we want to loop through all of the entries in the hash table. So in I is equal to 0 and less than prime num. And all we want to do is say at every entry in our hash table, every index is going to be equal to -1. That's not index, that's next index. And that's going to tell us that the slot is empty when we check that. And then every next is going to be equal to null because we don't yet have any nodes that will follow this. This is going to be the first node. Okay, so that should be it. That should initialize our hash table. We talked about two loops, right? The first loop to fill our hash table. We talked about the second loop, which was to check hash table for corresponding pair. Okay, so to fill our hash table, we're gonna probably have to loop through all of our numbers into I is equal to 0. I is less than num's size. So this is the array of numbers that we have that we want to fill our hash table with. And we're probably going to want to store the hash number, which we get from our hash function. So to get our hash number, we call our hash function with the actual number in our array, right? So that will give us a unique hash number. So once we have our hash number, all we need to do is fill our hash table. So first of all, if a slot in our hash table is empty, we can simply fill in that slot. And if it isn't empty, it means we already have something there, right? Which means we need to start creating a linked list from there. So the first case, we can simply say if the hash table at hash num, and if the index, as we described before, is equal to -1, meaning it's empty, then we know that the slot is empty, and we can just fill in the hash table entry, the node, right? Index is going to be equal to the current index of the array. Okay, if it's not empty, we're going to have to create a linked list from here, and we're going to have to stick a new node on the tail. So slot is not empty, and we need to create a new node to hold our data. So we're going to say node, let's call it new, is equal to struct node. We need to get some more memory. So we'll say size of node, struct node. And once we have our new node, we can just fill in the information in our node. New index is going to be equal to I, and new next is going to be equal to null because this is going to be paired at the tail of our linked list, so there's not going to be anything afterwards. So now we need to loop through our linked list, however big it is right now, and get to the tail. So we'll probably need some kind of pointer, some kind of temporary pointer to our linked list, to the current entry in our hash table rather. And that is going to point to one of the very first node at that entry. And what we want to do is we want to keep looping or keep traversing it until we reach the end of the linked list. So until temp next is not equal to null, I think that's right. We want to say, no, I probably don't need these braces. Just temp next is equal, oh, temp is equal to temp next. Temp is equal to temp next. Okay, once we finish traversing the linked list, this loop should finish, and now we know we're at the end of our linked list, we're at the tail, so all we have to say is temp next is equal to new. We just added our new node at the end of it, and that's it. We filled our hash table. Okay, now all we need to do now is the second loop. So in the first loop, by filling our hash table, we simply pass the number into our hash function. Now to find, now what we want to do is look for the corresponding number to this number, and we know to get that we had to take the target and subtract this number. So it's going to be pretty similar. So what we want to do is loop through our numbers again and look for the number which will be our corresponding pair. So in I is equal to 0, I is less than num's size. Just looping through all these numbers again. And this time hash num is going to be equal to hash function target minus nums, right? The number that we're specifically looking for. So our hash num is going to look in our hash table, and if there's actually an entry there, it means that we know we have a corresponding pair. But first of all, there might not be a corresponding pair. If there isn't, then we know that the index at that node is going to be -1. So we should probably just check for that first. Let's imagine that our target is 9 and the number that we had in our array was 6, for example. Well, 9 minus 6 would be 3. So we'd be searching for the hash number of 3 in our array, and 3 wouldn't be there, which means we never would have filled an entry for it, meaning it should be empty. So how do we do that? Well, we would look in our hash table, hash num, and we'd say if the index is equal to -1, then we know we don't have the number we're looking for. So we can just continue on to our next number. Okay, so now that we know that we do have the number we're looking for in our hash table, we need to find it and use it, right? It could be the first entry in a linked list in our hash table, or it could be if we did create a linked list along the line somewhere. So all we need to do to check the first entry is now we need to see that if the number in the array is the actual number we were looking for, then we found our corresponding pair. So to look in the array, we need to look at what the index is in our hash table. So hash num dot index, and we need to make sure this is equal to our target minus our nums I, right? And if these are equal, we know we've actually found a pair of numbers which equal our target. But we need to do one more check. We need to make sure that the same element isn't being used twice here. We could be checking the same index. So let's just make sure we're not checking the same index. So we would just check the index this time, and we'd make sure that it isn't equal to the current index that we're at in the array. So now we know that we found our result, our answer. So we can fill our result array with our numbers, with our indices. So result 0 is I, and result 1 is going to be equal to our hash table hash num dot index, right? Okay, and now we can just return our result. Return a result. All right. If we don't find it at the first entry, we're going to have to traverse the linked list that we created at this entry. It's along somewhere in our linked list. So we're probably going to need a pointer again to point at our individual nodes. And we've already checked the first node, so we can just start looking at the next node. And to do that, we would say hash num, and we'd look at the next node. And now we want to loop through each node until we find the number we're looking for. So temp is going to be not equal to a null. And so we kind of want to do the same check we did here, but instead of looking at the hash table entry, we already have the actual node that we're at. So we can just say temp index target is equal to target minus nums, and here again it will be just temp index. Okay, so if we pass this check, it means again we found our answer, so we can fill in our result array with our indices. Result 1 is equal to temp index. And again, we can just return our result. And just so the compiler doesn't complain, we probably need to put this here. And that should hopefully be it. So our time complexity is a lot better than our last algorithm, which was quadratic, right? Now all we have is these two loops, and both loops loop through the size of our array. So it's 2n now. It's 2n, but really that gets simplified in big O notation to O of n. So much better. Space complexity, it kind of depends on how many elements we have in our array, but generally it's O of n because we need to store at least the number of nodes that we have uh, in num's size. There are some other things we need to do, but because this video is quite long, I'm gonna end it here. It'll be good to do this as like a homework exercise, but something, for example, we might want to check is kind of return values from malloc. If malloc fails, we probably want to exit the program and give a warning or some kind of message because malloc might not, the system, the OS might not have memory for us. Another thing that we definitely would need to do is we're allocating all this memory for our hash table, but we're not actually doing anything with the hash table once we've kind of found our result. We're not, it's our result is this array here. Our is this 2-byte array. Um, we would need to create a function to free all of this memory. It will be pretty simple. All you would have to do is traverse the hash table, kind of how we did in a couple of examples here, and you would need to free each node. But yeah, I don't want to do that here right now. It'll make this video longer than it already is. It'll be a good little exercise for you to do. Otherwise, yeah, I hope this video was helpful. Thanks for watching.